Welcome to Energy Frontier, the Wyoming Landscape podcast, hosted by Dr. Erin Phillips, Director of Cross-Cutting Programs and Acting Senior Director of Research at the University of Wyoming School of Energy Resources. The show highlights SER's role in supporting our mission to promote energy-driven economic development in the state of Wyoming.
Greetings, listeners, and welcome to this episode of Energy Frontier, the Wyoming Landscape. Today's guest is someone who spends his time solving some of the world's most complex hidden puzzles. He is a School of Energy Resources professor of Geology and Geophysics at the University of Wyoming, a Wyoming Excellence Chair, and a Nielson Faculty Fellow. And most recently, he was honored as the recipient of the Felix Chase Prize for his exceptional contributions to mathematical geoscience. Beyond these accolades, he is at the forefront of a fascinating intersection of rock physics, seismic inversion, and complex statistics. Welcome to the show, Professor Dario Grana.
Thanks for having me.
So, Dario, I'd like to start off by giving our listeners a little background. Please tell us about yourself and your journey to the University of Wyoming.
Well, thanks. Yeah, I'm originally from Italy, as you can tell from my accent. I grew up in a small town around about 50 miles southeast of Milan, where the Olympics are right now. I come from a relatively low-income family. I'm a first-generation high school student and then a first-generation college student, too. In high school, I discovered my passion for science, mostly mathematics and chemistry. And so I decided to major in mathematics. I always wanted to be a professor, either in high school or college, but I was really afraid of the uncertainty within the academic path in Italy. It's very challenging over there. And also, I didn't feel that I was smart enough or creative enough to do research in pure mathematics. I thought that I had to come up with a new theorem or something, and I was like, I don't know if I can do this. So I was offered a position in an oil company as a researcher in a team working on oil and gas exploration, and that's really where I learned geophysics. I was super lucky because that company had a consulting agreement with Stanford University for a special research project. They were working on overpressure boreholes in North Africa, essentially. And so at some point, my boss asked me to go to Stanford and take a look at the project and try to figure out what these super smart professors at Stanford were doing. So I went there a few times, and at some point, they asked me if I wanted to do a PhD. So in 2010, I moved to the United States. I moved to California. I got my PhD in 2013. And then I started my position here at the University of Wyoming 15 days after getting my PhD, which was super intimidating. And so that's where my academic career really started.
Great. Well, like you said, you've been at the University of Wyoming now for 13 years. And in that time, you have been teaching, conducting research, and have even served in an administrative capacity, serving as the department head for Geology and Geophysics a couple of years ago. What would you say is your favorite part of working in higher education, and why?
For sure not the department head part. No, after 12, 13 years, I still think that the best part is working with the students. I mostly work with masters and PhD students. My research is really interdisciplinary. We combine mathematics, statistics, computer science, and geoscience. And so I require a certain background from the students. So it's a little bit easier to work with graduate students just because they have that kind of background. But master's and PhD mentoring is really the best part of the job. Seeing them growing into scientists and beyond where they started, shaping their future in a way, not just working on scientific projects, is for sure the most exciting part of the job. And seeing them succeeding in life afterwards is probably the best part, or at least in their career. My first student ever, Xiao Zhang, she now works in artificial intelligence and machine learning in the Bay Area. Mohit now works for NVIDIA, the software company in Seattle. And then some others went to academia. So one of my first students, Ming Liang, is now a full professor back in China, which was his dream as a kid. There are a couple of students that I co-advise, working working more on environmental geophysics. One is a lecturer in Australia. One is an assistant professor in Connecticut. So all these stories, they make me feel proud of the research group that I built. And I can see the enthusiasm of the students. Like, I was recently in China to give a lecture, and my lecture started at noon on a Sunday, and I think I ended up going back to the hotel around 9:30 p.m. There were students lined up asking questions, and some of them wanted to take pictures, which was a little bit surreal, but it was certainly exciting. So that's for sure the best part of the job.
Great. Well, I know you've had a lot of positive impact on the students that you've mentored. So let's talk a little bit about your research and field of study. Mathematical geoscience can sound a little intimidating to the layperson. So how do you describe the art of using math to learn about rocks?
It sounds intimidating, but the idea is relatively simple. So in our research, we want to understand the structure of the subsurface because we want to find energy and natural resources, oil and gas, water, CO2, whatever we're interested in. The problem is that we cannot directly measure the properties in the subsurface. For example, we would like to estimate how much oil and gas there is in a certain reservoir, but we cannot drill every 5 feet in order to find the answer to our questions. It's too expensive, it's not environmentally friendly, and so on and so forth. So because we cannot measure what we care about, we measure some other properties at the surface, for example, seismic data or electromagnetic data, so very complex data sets. And then we apply mathematical geoscience methods to translate the signals that we actually measure into the properties of rocks and fluids that we actually care about. And so at the end of this complicated process, we build three-dimensional models of the subsurface, and we provide these models to oil companies, service companies, stakeholders in the state of Wyoming, such that they can make informed decisions. For example, we could say, in this specific location, there is a spot at this X and Y coordinates where we have high probability to find oil and gas. And so the company can decide based on the probability if it is worth drilling a well or not, or if they want to drill 5 wells, and so on and so forth. So the mathematical geoscience part that I focus on is often called rock physics. Imagine that a rock is like a piece of cheese where we have a solid face and then we have some holes, or a sponge, for example. And so the oil and gas tend to infiltrate in these pores. And so one of the goals of rock physics is to quantify the amount of pore space, the volume of the empty space, because potentially it could be filled by oil and gas. So we try to build all these complex models that link these properties here that we care about, the pore volume, the oil volume, the gas volume, to all those measurements that we make at the surface. So the mathematical models essentially that we use in geoscience, they connect what we measure to what we want to predict to make informed decisions.
All right. Well, you mentioned seismic data, and seismic inversion is another of your areas of expertise. Will you give us a 10,000-foot view of what seismic inversion is and why it's important?
Yeah, seismic inversion is one of the most common tools in oil and gas exploration. The idea is that we want to measure some data at the surface. So at the surface, we place a huge amount of sensors, say every 50 feet in each direction. And then somehow we have to create a signal. So the easiest way would be to take a hammer and hit the rocks with, or the surface with a hammer. Oil companies, they have more powerful tools. Generally, they are vibro-sized trucks. So what they do is that they drive these trucks in the field, and the truck has a platform that they slam on the surface. This action creates a seismic wave that is propagated in the subsurface. So the seismic waves, they keep moving, and that's exactly what happens when there is an earthquake, essentially, just at a much smaller scale, much smaller magnitude, of course. So what happens is that we propagate these seismic waves, and the waves, they keep traveling in the subsurface until they find something strange happening. For example, a transition between one rock type to another rock type, or a transition from a rock filled with water with a rock filled with gas. And so when there is this kind of transition, part of the wave are reflected back to the surface, and they're measured by these sensors at the top. So the signal that we measure, the acquisition is relatively complex, but the signal that we measure is relatively simple. It looks like a seismogram when we have a really small earthquake, or an EKG. So you have something flat, and then there's a wiggle, and that wiggle represents an anomaly in the signal, and that's what we are interested in. And so the reason why we do seismic acquisition and inversion is that different rocks and different fluids, they have different seismic responses, so different seismic waves. So for example, if you have a reservoir filled by methane, the velocity of the seismic waves is generally relatively low. So if you look at a seismic map or graph, you generally see, and there is a gas reservoir, you generally see low velocities coming after a high velocity. So when you see that anomaly, that kind of delayed signal, it means that there's something that an oil company could be potentially interested. So the idea of the inversion part, which is the mathematical model that we apply, is to take these signals that look like the EKG or the seismogram for an earthquake. From these signals, we compute the velocity of the seismic waves, and the velocity of the seismic waves depend on the pore volume and the saturation. And so essentially, we use this tool to identify potential zones for drilling and extracting oil and gas, and so on and so forth.
Great. So some pretty powerful tools to understand the subsurface. And thanks for that. I really appreciate those really accessible explanations of complex procedures. So Dario, you're a really prolific author and have published many peer-reviewed articles, books, and more. Who would you consider to be the biggest target audience for your research?
Yeah, the focus of our research is to improve the understanding of the subsurface, and mostly for energy exploration. So the biggest audience has been oil companies and service companies as well. So the idea is that we want to improve the methods that are currently used to reduce the error in the predictions, such that whoever makes decisions, oil companies, stakeholders in the state of Wyoming, they can actually be more confident about the decisions that they make. So for example, if an oil company wants to drill a well, they would like to have a really small margin of error when it comes to finding hydrocarbon or the thickness of the reservoir and so on and so forth. So our idea for the last 12 years essentially has been take the models that we currently build and try to reduce the error more and more. So we started with models that had an error of 5%, and then now we are at 3%, and the goal maybe is to get to even more accurate models. So this kind of research is relatively applied in the sense that we understand relatively well the processes and the mechanisms that control the reservoir production, but we would like to improve the characterization such that we can make more informed decisions. The focus of the book is more for teaching purposes, to make this kind of really complicated models accessible to students and early career scientists. So we want to make these complex mathematical models understandable to a larger audience, to try to increase the interest in this kind of research. So I guess that we have two goals here. One is to provide more efficient and more accurate tools to oil companies, but we also want to explain and teach these methods to a broader audience of students, such that these complex models are accessible to not just geophysicists, but also geologists, geochemists, and petroleum engineers, and so on and so forth.
Very good. Well, this is a big picture question. What are some of the driving questions and the cutting edge research problems that you're trying to solve?
Yeah, so In a way, we talked about improving the models, but in a way, having better models is not enough. One of the key features of our research is what we call uncertainty quantification. So we build models, but then we also want to provide some kind of measure of the uncertainty of these models. So for example, the typical industry workflow is to predict the pore volume and the oil and gas percentages in the reservoir. And this could be applied also to mining too. It could be mineral concentrations. It could be applied to groundwater as well. So maybe we're interested in the amount of water in the aquifer that can be used for agricultural purposes. But the idea is always the same. We measure some data and we want to predict these quantities here: pore volume, oil percentage, gas percentage, and so on and so forth. What we're trying to do in our research, which is relatively unique, is we want to provide a number for these properties, but we also want to provide some kind of range of uncertainty about our predictions. Our models are not perfect. We try to be as accurate as we can, but we also have to compromise the accuracy with the computational cost. Ideally, if I had a supercomputer that I could run for 6 months, I would probably be able to build a more accurate model, but it's not possible. So what we do is we provide models with some numbers, and we also provide models with a measure of how wide the range is. Subsurface models are particularly uncertain because the data are always noisy, they're incomplete, they're not perfect. So what we want to do is to provide property estimates plus uncertainty. So we would like to say at this specific location in Wyoming, we're about to drill a well. We think that the reservoir is going to be 5,000 feet deep, but it could be 4,900 or 5,100. We're not sure about that. Typically, the depth is something that we're generally accurate. But then we have to estimate the pore volume. It could be 25%, 28%. So we try to make the decision-making process more informed by providing some ideas of some measurements of the uncertainty as well.
Great. Well, Dario, you've touched a little bit on the intersection between academia and industry, and you've also started the Bayesian Learning Consortium at the University of Wyoming, which is an industry-sponsored consortium to develop innovative quantitative methods to improve the characterization of subsurface reservoirs. Will you talk a little bit about the importance of collaborations between academia and industry in accelerating solutions to our real-world challenges?
Yeah, we started the Bayesian Learning Consortium in 2020. We now have 3 sponsors, 3 oil companies, BP, Petrobras, and Eni. The focus of the consortium is to improve the reservoir characterization and also the uncertainty quantification in the reservoir characterization. So there are 2 main goals. One is to quantify uncertainty for decision makers, and the other one is to learn from the data that we acquire. So the first part is the Bayesian part of the name of the consortium. Bayesian methods are statistical methods to quantify uncertainty in our predictions. And the way we do it is to combine some prior knowledge that we have, typically from geology, with the physics that is associated with the data. And so Bayesian methods, they aim to provide estimates of the uncertainty in our models. The second key innovation is the learning part. So for decades, we relied our methods on the physics that we know. So in my case, we work mostly with seismic data, sometimes with electromagnetic data. We know everything about the physics. We know how seismic waves or electromagnetic waves, they propagate in the subsurface, and we know what causes changes in the velocity of the seismic waves and so on and so forth. So the physics can tell us a lot about the subsurface. But there are things that we don't completely understand. For example, we really don't know when we have reservoirs, carbonate reservoirs with a lot of fractures, we don't really know how seismic waves react with fractures. So what we're trying to do is we use the physics, but on top of that, we try to take data sets from all around the world and try to learn from the data. This is the learning part, which is called either machine learning or deep learning. In our case, we do Bayesian learning because we want to do it in the probabilistic setting. So what we do is combine the physics with data science or machine learning such that we can extract information from the data that we cannot get using physical models. And so in this perspective, working with oil companies is really important for us because they have fantastic data sets that academia cannot acquire just because of limited funding. And so we can try to see if what we can learn combining physics with data mining or data science. And that's essentially the goal of the consortium. So we have approximately funding for $500,000, which allows us to hire students who can work on complete data sets, develop new methodologies. And then these students, in many cases, they do internships and they go to work for oil companies. So there's a clear interaction between academia and industry in this setting.
Yeah, sounds like really great opportunities for our students. So now to a topic that's on many of our minds. Looking toward the future, how do you see AI impacting geophysics and your work?
Yeah, AI will be for sure predominant. Right now, we're in geosciences. We're mostly using a subset of tools of AI that we refer to as machine learning or deep learning. We don't use all the available tools of AI yet. But the use of machine learning is becoming more and more important and relevant in our field. The idea is that we want to learn from the data. So just to give you some examples, when you drive on a highway and there's a camera that captures your license plate, that's an example of application of machine learning. Essentially, the camera takes a picture, but the picture is often blurry. It might be taken in severe weather conditions. The car might be speeding. So typically, these pictures are relatively blurry. So machine learning algorithms, they take these pictures and they convert them into a number, the license plate. And we try to do something similar in the subsurface. We take these massive seismic data sets and we try to convert these wiggles that don't have any physical meaning apparently into models of properties that we care about. When it comes to geoscience, it's a little bit more challenging because we have a lot of knowledge about the subsurface without using any machine learning. We know a lot about geology, thanks to my amazing colleagues in the Department of Geology and Geophysics and in the School of Energy Resources. We know a lot about the physics, and so there are concepts that we already know, and then from time to time we find these data sets where there are anomalies that we cannot explain. That's where machine learning can really help combining data with prior knowledge. It's a little bit more difficult than the example that I brought up earlier on about the license plate. When it comes to the license plate, what they do is typically take a huge amount of pictures of license plate that they know. So essentially, there's one person taking literally pictures of the license plates, some blurry, some are not, and then they know the license plate, and so they train the algorithm in order to be able to make predictions when you are on the highway or at a toll booth or whatever. In our case, we have a lot of data, but we don't know the actual truth. So in the case of the license plate, you know it when you build this training data set. In our case, we really don't. So that's where you have to combine the prior knowledge of geology and physics with machine learning. So I think that this is going to be one of the main directions for the future. There are already some methods out there called physics-informed neural network. One of my PhD students did his entire PhD on that topic. Now he's a postdoc at Stanford working on similar methods, but in the mining field. So.
All right. Well, thanks for that. Dario, now I want to put you on the spot a little bit and talk about some of the major accolades you've achieved throughout your career. Most recently, you received the Felix Chase Prize for your contributions to mathematical geoscience, which is a really big deal in your field. For our listeners who are likely unfamiliar with this award, it is administered by the International Association for Mathematical Geosciences and is presented to recipients for their outstanding contributions to mathematical geoscience or related applications of mathematics or informatics. So first of all, congratulations. This is an incredible honor. And Dario, looking back at your body of work, what do you consider the pivotal breakthrough that best represents why you were chosen for this honor?
That's probably the most difficult question because I really don't know why I won the award. I might have been the only candidate, I'm not sure. But I think that there are two main achievements in my career. One is more on the statistical or mathematical side and one more on the geoscience side. So for the mathematical approach, in our group, we developed something. It has a really fancy name. It's a little bit intimidating, but it's relatively simple. It's called Bayesian-Gaussian mixture inversion. So what we do is essentially take massive data sets, try to predict properties that we care about. That's the inversion part. We do it in a Bayesian way, which means in a statistical way. So rather than just saying porosity is equal 25%, we say porosity is 25% plus or minus 3%, for example. And the Gaussian mixture part is really what made our research group stand out compared to other research groups, because we actually use very complex statistical models. So we don't have to make the assumptions that, for example, there's only, if you look at the distribution of porosity in the subsurface, there's not just one peak. There can be multiple peaks corresponding to different rock types. And so that was one of the achievements of our research group. Probably the most popular publication on this topic was the one in 2017, which was in collaboration with a university, the Department of Statistics of the University of Trondheim in Norway. The second biggest achievement in our research group is the integration of rock physics into seismic inversion. So for decades, the oil and gas companies relied on seismic inversion as a tool to take seismic data, compute seismic velocities, so the velocity of the seismic waves that propagate in the subsurface, and then geologists try to interpret these velocities in terms of geological properties or rock and fluid properties. So high velocity meant that the rock was really stiff, so probably not a good reservoir. Low velocity meant that the rock was relatively soft, so probably a lot of porosity and potentially lots of fluid. But this was a qualitative interpretation. There might be rocks that are very fast, but they still have fractures and they might contain oil and gas. That's something that happens all the time in reservoirs in the Middle East, where the rock is a carbonate rock, really tight, high velocities, but there's still oil and gas. So the interpretation required a lot of prior knowledge. What we try to do is to make this interpretation a little bit easier for geologists. So instead of predicting velocities of seismic waves, we predicted exactly the properties that geologists like to look at: porosity, permeability, oil and gas saturation. So this was a project that started as a collaboration with an oil company in Italy, Eni. That was one of my first publications. We continued working with a university in Portugal and a university in Brazil to develop these training data sets that could be used to learn something about the properties of interest. And now my research group is mostly working on this kind of problems. So to go back to the award, I guess these are the two reasons why I got the award, but I should really share the award with all my students because they are the ones doing the work. I just have the privilege to go around the world and present the results.
Excellent. So Dario, you have also received multiple awards for your teaching and mentorship, and it's rare to find someone who is equally celebrated by the world's top researchers and by a classroom of students. So how do you balance these two worlds and this responsibility?
Yeah, teaching is really the reason why I chose academia in the first place. When I was in high school and even in college, I didn't even know what a PhD was, and I didn't really know that professors at the university, they would focus on research. So to me, a university professor would be a person who goes to the classroom every day. Well, I was a mathematician, of course, so my dream was to be in a classroom with 6 chalkboards and just writing equations constantly for like 8 hours during the day. That's what I thought my job would have been. Then, of course, throughout the years and with a lot of mentoring from amazing mentors in Italy and in the United States, I learned that being a professor means combining research, teaching, mentoring, and so on and so forth. But teaching was my passion when I started. It is still my passion now. The most exciting part about teaching to me is trying to make complex ideas accessible to all the students, no matter what their background is. So there's a constant effort in my classes to bring at least simplified versions of our research activity into the lectures. So, of course, I cannot explain all the complex mathematical methods that we do, because some of the undergrads might not have the mathematical background or simply they just don't have the experience to understand these concepts. But we try to at least bring a simple example where we show a borehole, we show a measurement, like, for example, density, and we show them how to interpret this density measurement. So, for example, when you see very low density that goes below, say, 2 grams per centimeter cube, it means that the porosity is very low. Most likely the fluid is gas and it's not oil. When you see porosity that spikes up to maybe 2.7 or 2.8, it means that you are in a very stiff rock, so the porosity is going to be really low, and so on and so forth. This is a simple example of inversion or mathematical methods that we use in our research, but we bring it to the classroom to make it accessible to students and to try to spark curiosity in what we do. The more complex the research is, the more challenging it is to make it accessible and also create some enthusiasm. It could be a little bit demoralizing to go to a class where you have to face really complex problems without having the right background. But if we are able to simplify the problems and try to show them a path towards these complicated complex models, then from time to time we get a lot of enthusiasm and a lot of interest from the undergrads.
Well, it sounds like you're really bringing those real world examples into the classroom, which is just so important. So let's turn to Wyoming. In an energy state like Wyoming, your work has the potential to make a real impact. Do you have examples of success stories that your research has contributed to here in Wyoming?
Yeah, when I started my position in 2013, I came with a clear plan of some research projects that I wanted to work on, mostly unconventional reservoirs. So for my entire career in the industry and as a PhD student at Stanford, I focused on conventional reservoirs. So the idea was we look at reservoirs like in the Gulf of Mexico, where the reservoir rock is typically a sandstone, granular media, high porosity. And so the idea was to develop physical relationships such that we could take those seismic data sets that we talked earlier on and convert them into porosity, fluid volumes, and so on and so forth. The idea was to use the same methods here in unconventional reservoirs in Wyoming, for example, gas shale. The physics of gas shale is still partially unknown, or at least the way seismic waves respond in this kind of reservoirs. So that was my first original plan. In 2014, the oil gas dropped, so funding for this kind of research was kind of limited, but there was a lot of interest in CO2 sequestration, so we tried to apply the same techniques to CO2 sequestration studies. So for those who are not familiar, CO2 sequestration means essentially taking CO2 that is emitted from, for example, a power plant, compress it into a liquid state and then inject it into the subsurface. So essentially, in a way, it's the opposite of what we do in oil and gas. In oil and gas, we extract oil and gas from a borehole. In CO2, we inject it. Actually, in many studies, we do both. We actually inject CO2 in order to push the remaining oil towards the production well. And so I started to work on these kind of problems, and probably our most successful study was the Rock Springs uplift. So this was a project funded by the Department Department of Energy in 2014. The project was led by Professor John Kazuba in the Department of Geology and Geophysics. And the Rock Springs Uplift is a formation near Rock Springs, near the Jim Bridger Power Plant, which is one of the top power plants for CO2 emissions. And the idea was to do a feasibility study where we could actually understand the structures of the reservoirs where we could potentially inject CO2. So we found two formations. One was thick but relatively tight, and one was thin but fractured with high porosity. So the idea was to do a study of subsurface characterization where we could take all the data sets that have been acquired in the area, seismic data sets, electromagnetic data sets, well logs, and so on and so forth, and try to build a three-dimensional models that could show where the CO2 would propagate in the subsurface, at what rate, how the reservoir would look like in 100 years, 500 years, and so on and so forth. And so that project led to several publications in our research group with several colleagues in the university. And I think it's a really good, it's a roadmap for this kind of studies on how to use seismic data and combine it with rock physics.
Excellent. So many different applications for the research that you do. So what other research areas in the energy and environmental fields that you are working on are relevant for Wyoming and the Mountain West?
Yeah, so throughout my career, I worked mostly on three different energy problems: oil and gas, especially in the first part of my career, CO2 sequestration studies, which can be used in combination with oil and gas productions because we can use CO2 as a fluid to improve and enhance the oil recovery, and then geothermal energy. So geothermal energy is probably the one that is the least known among these problems. The idea is that from a geophysical point of view, we use the same tools. So we used seismic data sets, we use electromagnetic data sets, and we use the mathematical models that we mentioned before in order to study potential geothermal sites. So we work with the Idaho National Lab for a feasibility study for a potential geothermal energy development. The idea is that we have a heat source in the subsurface, which could be, for example, the Yellowstone caldera, and then we have some fracture rocks. So if we actually inject water, the water is transformed into steam, and the steam produces energy. So what we want to do from a geophysical perspective is to acquire seismic data and develop rock physics models in order to improve the characterization of these reservoirs to understand the processes that control the energy production. Mostly we focus on what we call the brittleness of the rock. So we want to understand how easy it is to fracture the rocks in order to create this path for water to flow in the reservoir and then to produce steam and energy. So I don't think that this is going to replace oil and gas in the state of Wyoming, but it's for sure an increasingly important contributor to the energy sector. We also worked on environmental problems. So if you're actually driving from Laramie to Cheyenne, from time to time, you might see some students along Happy Jack Road that are measuring some data. So they put some sensors and then they hit the rocks with a hammer and they try to acquire some data. The idea there is to try to monitor the snow melt and the fluid flow of water underground. So when snow melts, it infiltrates in the subsurface and then it reaches an aquifer and it tends to flow down to the valley. There's less and less snow, as we can tell, just going at snowy range this year. And so the water that can be used for agricultural purposes has to be managed more carefully. So what we're trying to do is to use the same methods that we mentioned before, seismic data, electromagnetic data, electric data in this case, and rock physics models in order to monitor the recharge of the aquifers such that the stakeholders in Wyoming can make more informed decisions. So this project is led by Professor Andy Parsekian, but one of the key features that we're trying to develop is real-time monitoring. So instead of making a measure at the beginning of the year and the end of the year, we would like to have data every day so we can track where the water or the snow melt is going to go during the seasonal changes.
Well, it's always good to see geology and geophysics students out working on roadside outcrops in Wyoming. So that brings us back to one more question about your students. Many go on to work in energy, data science, or academia. What is the most important local lesson they can learn in your research group that they couldn't learn outside UW or the state of Wyoming?
Yeah, Wyoming is the best place to learn geology. So even though my students actually work on mathematical methods, we always have to make a connection between the methods and the predictions that we can come up with the actual geology. So in a way, the state of Wyoming is a natural lab for developing our methods. We can go out in the field, take pictures of the outcrops, compare our predictions with the models that we developed. And so that kind of knowledge is relatively unique in the entire states or in the entire world, really. And so the main advantage of our group is that we have a great knowledge of oil and gas reservoirs in the state of Wyoming, so the students can actually go and work for companies in the state, but they can also apply the same knowledge to other fields, and so they're ready for the industry job market where they can actually go from one company to another one and work on different fields and in different countries.
All right. Well, as we wrap up here, Dario, I'm going to give a little insight into our podcast. When we schedule a guest, we often ask experts in our building for suggestions on the conversation. And as our listeners know, we have a lot of geologists here in the building, many of whom are alumni of the Geology and Geophysics department here at UW. And the burning question that they would like you to answer is, are you the funniest professor in the Geology and Geophysics department?
I'm definitely the funniest guy in the Geology and Geophysics department, so the rumor is true. But I'm Italian, so it comes with the passport.
All right. Thanks, Dario. And one more question here. Thanks again so much for joining us today. We always end our podcast with your favorite thing to do or place to visit in Wyoming. But I'm going to ask you two final questions. Please tell us what you miss the most about Italy, and then what your favorite thing is about Wyoming.
That's a tough one. I guess I should say the Italian food is the thing that I miss the most about Italy, and I'm not offending anybody in the Laramie community since we don't have an Italian restaurant in Laramie, I guess. But no, the truth is that what I miss the most is the Italian architecture. So I was lucky enough to go to high school in Cremona and to university in Pavia that are really rich when it comes to Italian architecture. So the idea of taking a train, getting off the train at the train station and then walking around 17th century buildings is something that is probably the thing that I miss the most, in addition to my family, of course. But I love Wyoming. I have been here for 13 years. I think that the thing that I love the most is probably nature. My happy place is Snowy Range. I go there skiing. I go in the summer hiking. Lake Marie is probably one of the most beautiful places on earth, in my view. And I also like the small college town. I grew up in a small town in Italy, 227 people. So Laramie to me seems like Las Vegas, but it's just Laramie. But I really love how vibrant the community is, especially thanks to the university. There's always something to do. And so if I'm not hiking or skiing, then I'm probably walking around campus and just participating in students' life.
Well, you've lived in two very lovely places. So thanks again, Dario, and thanks to our listeners, and we'll see you next time.
Sounds good. Thank you.
Thank you for listening to this episode of Energy Frontier, the Wyoming Landscape, the podcast that highlights the School of Energy Resources at the University of Wyoming. You can expect a new episode of Energy Frontier every other Wednesday on Apple Podcasts, Spotify, or wherever you listen to podcasts. See you next time.